Hi guys, in this video we are going to talk about fifth disease. It was so called fifth disease because it was actually kind of the fifth classical childhood exanthem. So we had measles, rubella, chickenpox, roseola, and fifth disease. You may have also heard fifth disease referred to as slapped cheek syndrome. This is because the rash for this one literally looks like somebody went and slap the cheeks of these poor little kids because they get these bright red rashes on their face. This one and roseola are the two classical childhood exanthems that we may still see with some frequency, and that's because there's no vaccine. There's no vaccine for parvovirus B19, which is what causes fifth disease, and there's no vaccine for human herpes viruses 6 or 7, which cause roseola. But the other ones, ruby virus, varicella virus, and measles virus, we have vaccines for, so we don't tend to see those as often. Okay, this virus is tiny, like super tiny. So it's a very small icosahedral capsid, and it's got a single-stranded DNA genome. One of the things that's really unique about this virus is that it absolutely needs a growing or replicating cell. And part of the reason that is really important for you to know that is because what it really loves to replicate is erythroid precursor cells. And that's a huge part of the biphasic disease that we see with B19 virus. Most of the time, we actually see disease with parvovirus in late winter and spring. So, times when people are, still inside and around each other a lot. Okay. It is the major cause of erythema infectiosum, also known as fifth disease, slap cheek, etc. Most of the time, it's fairly benign, unless you have a couple special cases. Obviously, anytime we have an immunocompromised individual, we worry about that. But really, in patients with chronic anemia, it can cause aplastic crisis. So by chronic anemia, I'm really talking about patients with sickle cell, or anyone who has any sort of difficulty creating erythroid precursor cells, because basically parvovirus is going to shut down the creation of erythroid precursor cells for about a week. It also is very dangerous to the fetus. In pregnant women, it can cause hydrops fetalis, basically killing the fetus. So it's a very significant disease for pregnant women and their fetus. It is transmitted by aerosols and direct contact. So this is another one of those ones that kind of, runs rapid through child cares. There are actually two parvoviruses which cause human disease, B19 and BOCA. We're really only going to talk about B19. B19 is pretty common. About 65% of adults have been infected with B19 by the age of 40. So most of us at some point in our lives will contract it. It's really not that big a deal unless you have some sort of chronic anemia or you happen to be pregnant at the time. When we most often expect patients to contract it is when they are children or adolescents, typically ending around the age of 15 years of age is when the incidence starts to go down. And then if you do contract it as an adult, instead of the rash, you're more likely to experience arthralgia and maybe even develop a form of arthritis. This is all due to the immunopathogenesis of this virus. So basically the response we make to B19 virus leads to immune complexes. And those immune complexes deposit in the synovial fluid as well as in the skin. And that leads to the rash and the arthritis that is associated with the virus. All right, let's talk about the structure and replication of the parvoviruses. The parvoviridae are the smallest of the DNA viruses. Their small size and limited genetic repertoire make them more dependent than any other DNA virus on the host cell. And that's part of why they have such restrictive cell tropisms and why they really do prefer a specific type of cell. Basically, the B19 genome contains one linear single strand of DNA. And that's it. That's the whole genome. You can have a plus sense strand or a minus sense strand. That doesn't really matter. They're going to be packaged separately into virions. The genome encodes for 3 structural and 2 major non-structural proteins. And unlike some of the larger DNA viruses, the parvovirus must infect mitotically active cells. It needs a cell that is replicating. And that's why I say it's more dependent than any other virus on the host cell. Because if the host cell doesn't replicate, if it's, say, like a neuron, which replicates very slowly, then the virus is not going to be able to replicate itself. They basically, the reason they need this is that the parvovirus doesn't really encode its own polymerase per se. So it means that it needs to stimulate cell growth or a polymerase in order to be replicated. The other thing that's interesting and kind of makes sense with this very small genome is that there's really only one serotype of B19. So that serotype is the singular serotype. You would think we would be able to have a vaccine of that since there's only one serotype, but as far as I know, there is not one at this time. Okay, so how does it work? First off, B19 infects cells of the erythroid lineage. This would include things like fresh bone marrow cells, erythroid cells from the fetal liver, and erythroid leukemic cells. So basically, it does this by binding to the erythrocyte blood group P antigen. Okay, the P antigen is also sometimes referred to as globicide, and basically it's internalized, and the virion is uncoded, and then the single strand of DNA. I'm trying to find where we're at. So it comes in, it's uncoded, and then the single strand of DNA is basically released. All right, and at that point, it gets delivered into the nucleus for replication. Now, at this point, it needs the virus to enter it needs the host cell to enter S phase. If the host cell doesn't enter S phase, the host cell will not express the necessary factors that the virus needs in order to replicate. Namely, what it needs is the DNA polymerase. And that's really only active during S phase of mitosis. Okay, so these factors are only available then. So the cellular DNA polymerases are required to generate basically a complementary strand of DNA. So the single-stranded DNA strand is then converted to a double-stranded DNA strand version of itself. And that is what is required for transcription and translation. So then you're going to get inverted repeat sequences of DNA at both ends of the genome. And they're basically going to fold back, which is what I'm showing here, and hybridize with the genome to create a primer for the cell's DNA polymerase. And this creates the complementary strand and replicates the genome. There are two major non-structural proteins. I'm trying to see if they're on the image here, and I don't see them. But there's basically two non-structural proteins, and then there's also VP1 and VP2, which are structural capsid proteins. All of these are going to be synthesized in the cytoplasm. The structural proteins are going to go into the nucleus. You can see that's this here, where the virion is assembled. VP2 is actually going to be cleaved to produce VP3, and then the whole package gets kind of put together, and the cell lyses, and that releases the virions out. And the virions are only released upon cell lysis. So that's kind of the method this works. I'm not going to ask you to repeat to me the structure and replication. It might be helpful to know that it's a single linear, single-stranded DNA genome, and that it's a very small genome. And like I said, because it requires mitotically active cells, that's actually important for kind of the clinical syndrome we see. So it's very reliant on the host cell, and it likes cells of the erythroid lineage. All right, so I mentioned that it really likes erythroid cells, and it's actually cytolytic to erythroid cells. So this is part of what actually leads to the disease that we see in patients. Particularly, it actually likes erythroid precursor cells, which, as I mentioned on the previous slide, can be found from a couple different places. The rash and the arthralgia, which are associated with B19 infection, is actually created by the direct killing of these erythroid precursor cells and the subsequent immune responses to the infection. So one of the things that you can think about with this virus is that the immunopathogenesis for B19 and rubella, which is caused by the ruby virus, are actually really similar. Both of these cause immune complexes with the virion, and that's what leads to the rash and arthralgia that we see in both syndromes, or both clinical symptoms, right? All right, so how does it work? First off, initially the virus is going to replicate in the nasopharynx or kind of the upper respiratory tract. That's where it initially hangs out. Once the individual becomes viremic, the virus actually moves to the bone marrow. So once we're viremic, that's when we can actually access the bone marrow, which is where those erythroid precursors are found. And then it's in a nice happy home. Once it's in the bone marrow and replicates, it's going to kill the erythroid precursor cells. And that's really dangerous because essentially we're going to shut down erythroid precursor cells for about a week. It has a biphasic disease, okay? So the initial febrile stage, phase 1, during this time, the patient is infectious. The patient has this prodrome for about a week, which is basically characterized by, you know, normal viral flu-like syndrome, okay? And during this time, erythrocyte production is stopped for approximately 1 week because the viral killing of those erythroid precursor cells. You're going to have a large number of virion release about 8 days after infection, and that's going to lead to that flu-like symptom. And also what is going to lead to the formation of the immune complexes, which basically cause your second immune-mediated symptomatic stage. So in this stage, the patient will experience the characteristic rash and arthralgia, and it coincides with the production of virus-specific antibody. And that's the key, because in this stage, you get the virion. In this stage, you get the antibody. And when they come together, that gives you your immune complex, which actually leads to disease. Antibody will actually shut down the viremia once it's actually been produced, and actually is what leads to the resolution of disease and reestablishment of the erythroid precursor cell lineage. But it also contributes to the symptoms, because the symptoms of rash and arthralgia are actually due to the deposition of these immune complexes. So it's kind of a double-edged sword in that way. We're making a good immune response, but that immune response is contributing to the immediate disease. But it will save kind of the larger problem of destruction of your erythroid precursor cells. Okay, so let's talk about the different clinical syndromes. The first one is erythema infectiosum, which is fifth disease. In this case, the infection starts with just kind of an unremarkable prodrome, okay? So this is going to take place for about 7 to 10 days, and during this time, the patient is infectious, right? Because this is phase 1, and the patient is just churning out virions. Basically, as it destroys those cells, all those virions are released. Infection of a normal host may cause either no noticeable symptoms or fever and nonspecific symptoms like sore throat, chills, malaise, myalgia, as well as a slight decrease in hemoglobin levels as we have, less erythroid precursors. This period is followed by the distinctive rash on the cheek, which is what I'm showing here, that hand slap or slap cheek syndrome. The rash then usually spreads to the arms and legs, which I'm showing here, kind of this lacy rash you can see here. And that'll basically spread, and then it'll subside over the course of 1 to 2 weeks. In most patients, this is going to be fairly benign, subside, and then the patient is protected from it. In adults, instead of the characteristic rash, we actually tend to see a polyarthritis. Adults can get the rash too, but the polyarthritis can occur with or without the rash. And this one lasts much longer. It can last weeks to months, even longer in some cases. So you're going to see arthritis of hands, wrists, knees, and ankles. Those are kind of the main places. The rash may precede the arthritis or may not be there at all. And in some immunocompromised patients, this can actually be a chronic illness. All right, so let's talk about the two more serious things that happen as a result of B19. So the first is aplastic crisis. This is the most serious complication of parvovirus infection, and it occurs in patients with chronic hemolytic anemia, particularly sickle cell anemia, right? And in this case, what's really concerning is the loss of those erythroid precursors. So think about it. In normal patients, we get a transient decrease in erythropoiesis in the bone marrow. That's okay. We can handle that. We have, a transient decrease in hemoglobin, and it's okay. But if you have a chronic hemolytic anemia, you're already without as much hemoglobin as you need. You're already having trouble moving oxygen throughout your body the way you need to. So this resultant reticulocytopenia, which lasts for about 7 to 10 days and is, kind of uncomfortable and benign in your average patient, is actually a crisis in a patient with a chronic hemolytic anemia. So in this case, you'll get aplastic crisis, which is accompanied by fever and the flu-like syndrome. The other serious complication is fetal hydrops. B19 infection of a seronegative mother increases the risk for fetal death. The virus may infect the fetus and basically kill the erythrocyte precursors within the fetus, causing anemia, edema, hypoxia, and congestive heart failure, which is hydrops fetalis. If you have a seropositive woman who becomes infected with B19 while pregnant, there's no adverse effect on the fetus, and it does not appear to cause any congenital abnormalities in that case. The likelihood is that mom has antibodies that then protects the fetus and everything is fine. But if the mom was seronegative and becomes infected, mom will be fine, but the risk to her fetus is very significant. To diagnose B19, you really just look for clinical presentation. I mean, that rash is pretty distinctive. You can also do serology. Serology is actually useful when we think about fetal hydrops. You can actually, if you have an exposure risk of a pregnant woman, then you can actually see what their serology is to kind of give them some peace of mind. This was the case of a family member of mine who actually is a school teacher. While she was pregnant, one of the kids in her classroom developed B19 or Fifth disease. She went in, had her serology done, thankfully had a very high titer, and her and her baby were fine. You can also do PCR, but most of the time it is not necessary because you can do clinical presentation. There's no vaccine, and really the only thing we can do for this one is supportive